In this video, we will go over the details of the original cryptocurrency implementation, Bitcoin. Let's first look at the Bitcoin transaction lifecycle. Alex opens his Bitcoin wallet. In this wallet, Alex has all the money that he can theoretically spend. Alex now wants to spend some of his money by sending it to Sonia. To do that, he scans or copies Sonia's address. This is Sonia's public key. He then fills the amount that he would like to send and decides what fee he wants to give for this transaction. He then sends the money. So look at how Alex is in control and determines the transaction fee that he wants to spend. Once Alex has entered Sonia's address, entered the amount of money he wants to send, and the transaction fee that he is willing to pay, Alex's wallet software signs this transaction with Alex's private key and sends the money to Sonia's public key. When this and other such transactions are propagated to all the Bitcoin nodes, we have nodes called miners who start solving the puzzle, and they want to take these transactions and add them to a block. In order to create a block, miners have to go through a computational process where they are trying to find out a certain hash, and we will describe that in more detail later. Once the hash is found, the mining is completed. This block is now transmitted to all the other nodes. And once this block is verified by each node, it is added to the blockchain. Once the block with Alex's transaction is added to the blockchain, Alex has successfully sent the money to Sonia. Sonia now has this money available in her wallet, and whenever she applies her private key to this money, she will be able to spend it. So let's step back and look at the components of Bitcoin. So first of all, we have a transaction. The transaction, as in the example we just saw, was from Alex to Sonia. It had Alex's public key and it had Sonia's public key. The transaction was signed by Alex's private key, and the condition for Sonia to spend the money was that she needs to have access to her private key. And if she does, then she can spend the money. So now what is a block? A block is just a list of transactions. And the block has something called a block header. A blockchain is several blocks connected together. The key thing here is that the block header for block n has a connection to the block n-1 header. And the node that will add the block n+1 will have in its header a connection to the block n header. It is these connections that maintain the chain. If we want to change anything in the block n-1, we would have to change block n as well as block n+1. This is what makes it very difficult to make any changes to a blockchain. Any node in a Bitcoin implementation has 4 components. The first is the wallet. The second is the blockchain, which is the distributed ledger. The third is the miner, which is trying to discover the hash. And the fourth is the network. This is the piece of software that does the peer-to-peer communication with other Bitcoin nodes. So any Bitcoin node can have all these 4 components, or it can choose just to have the wallet, or it can choose just to have the blockchain, or it can choose just to have the mining. So this way, the Bitcoin nodes in the Bitcoin network can decide what functions they want to perform, and theoretically, they can perform all the 4 functions. Let's go into some more detail. Let's look at a Bitcoin transaction. Bitcoin transactions consists of all the inputs. This is all the money that we want to spend. Let's say in your wallet, in your physical wallet, you have 2 $5 bills, one $10 bill, and one $1 bill. Let's say you want to spend $17. You will need as your input the $10 bill and 2 $5 bills. Only then can you spend $17. Now your output will be $17 to whoever you want to give that money to. You have $3 in change. So you want to give yourself back $2, and then let's say you want to pay $1 as a transaction fee. You'll have 3 inputs, $5, $5, and $10. You'll have 2 outputs. One will be the $17, and one will be the $2 back to you. Now the difference between the outputs, which is 19, and the inputs 20, becomes the transaction fee, $1 in this case. An input into any transaction has to be an output of some other transaction. This is how we keep an audit trail or provenance of all the money. Now, there is a specific type of transaction which we call the coin-based transaction. The coin-based transaction is such that it does not have any inputs. It only has an output. This is given as a reward to the miner node that finds the hash. That's called the mining reward, and it's also called the coin-based reward, or it's also called the block reward. In this case, we're kind of creating money. We are mining money. So there's no input, but there's just an output which goes to the miner's address. So you see how every time we spend money, we have inputs and then we have outputs. And by the way, every input has to be an output of some previous transaction. So at all points in time, we are creating an audit trail of where the money came from and where it is going. So if we have an input, we should be able to trace to the output where that money came from. The input represents money that can be spent only if the private key specified in the output transaction is available. That's how we validate that this is money that can be spent. So we sometimes call this triple entry accounting because we can basically trace money from its source to wherever it's being spent and wherever it's going to be spent. It's pretty cool. Like, we can actually see our economy and all the value exchanges in one place. Now let's look at the transaction data structure. We have the input transactions and we have the output transactions. And what happens is every input transaction has in it the address of the output transaction it came from. So we can quickly verify it, and it has the condition, the terms, the smart contract, if you will, for spending the money that needs to be available before the money can be spent. So that's how we enforce the validity and the verification of the input and the output. Now, the language that is used in Bitcoin for specifying all these terms is called Bitcoin script. It's a very simple language. So the types of terms that we can have in Bitcoin are very limited. So now let's look at the block header. What a block header consists of, and this one is important. We have this notion of a hash of the previous block. So that's how in block N, we create a link to block n-1. We have a hash Merkle root. I'm going to explain this in a minute. We have n bits and we have n nons. N bits gives you the difficulty of the hash that a miner has to find. N bits represents the number of leading zeros that a hash should have for it to be a valid hash. N nons is the number that a miner can manipulate so as to find a valid hash. This is how mining works. In Bitcoin, we need to find a hash of everything in the block header. The N version of the blockchain software, the hash of the previous block, the hash Merkle root, the N time, N bits, and N nons. N bits is fixed, so we want to find a hash that has as many leading zeros as specified by N bits. The only thing a miner can do is change N nons. So what a miner does is it sets an N nons and computes a hash. We've learned previously that computing a hash is very, very efficient. But this hash might not have the number of leading zeros we want. So then we have to change the N nons and do it again. Change the N nons and do it again. And eventually we find the hash. Once you found the hash that satisfies N bits, any other node can very quickly check if it has the correct number of leading zeros. That's why the hash is hard to find, but the hash is very easy to verify. So when we have a block header, we can find its hash, and that hash becomes the hash of the previous block in the next block. What's the Merkle root? The Merkle root is the hash of all the transactions in a block. We take 2 transactions at a time and we hash them. And we keep doing that until we get one hash, and that is the hash that is called the Merkle root hash, which represents the information contained in all the transactions. So in a way, we've reduced the volume of all the transactions into this hash that we put in the header. So how does Bitcoin mining work? It's the process of adding new blocks to the blockchain. Nodes broadcast transactions that they want captured in the blockchain. The miner nodes collect some of these transactions into a candidate block. The miner nodes have a list of all the valid transactions, and they select which of those transactions they want in a block. And by the way, they do that to maximize their transaction fee. And the miner nodes then creates the block header by computing the hash Merkle root, which is easy, and finding the N nons that now meets the difficulty level specified by N bits. The process of finding this hash is known as proof of work. The miner node transmits the block with the N nons that it has found to all the nodes. The other nodes can quickly verify that the block is valid and add it to the blockchain. What's the block addition workflow? Nodes broadcast transactions. Mining nodes collect the valid transactions. They reject the invalid transactions, and they extend the latest block. Miners compete to discover the N nons that will give them a valid hash. Once they've discovered the hash, they broadcast the node. Whenever a node receives a block, they stop working on mining the block that they are working on. They add the block they have received to the blockchain. They then revise their list of valid transactions and start working on mining the next block. So how do payments work? Let's say a merchant has shared the address that they need to be paid at. If I am buying from a merchant at time t, I will initiate a transaction at some point. This transaction will get added into a candidate block. And once that is done, the merchant can wait for confirmation that the transaction is added into a block. Because once a transaction is added into a block, it is very hard to change it, and the merchant can ship the goods to me. You should know that at any time, multiple nodes could have discovered the hash, and they send their blocks with a valid hash out. Different nodes will receive different blocks with valid hashes. They're going to just receive the block, and what they're checking is, am I attaching it correctly in the right place? They will keep doing that, and every once in a while they'll get a block that can be added, but it's not in the right place, and they then reject it. We call this the theory of the longest chain, and this kind of goes back to the notion of eventual consistency. There are times when the nodes can have conflicting information about the blockchain, but we know that eventually they will get consistent. Lastly, how often are new blocks created? In Bitcoin, blocks are created every 10 minutes or so. Now, what the Bitcoin software does is after 2016 blocks have been created, it evaluates what was the average time it took for the miners to create a new block. If this time is greater than 10, then it makes n bits easier so that people can find the blocks quicker. It reduces the number of leading zeros. Then if the average time is less than 10 minutes, then it makes the pattern harder. So we increase the number of leading zeros, and that's how we make sure that blocks are created every 10 minutes. Why don't we want to create blocks more often than 10 minutes? Because we want to decrease the chance that the nodes will get out of sync. And that's kind of the design trade-off we make. So we've got a very quick overview of how Bitcoin works. When we get together, we can discuss your question in more detail. For now, you should try to absorb this, and then we can discuss in our live session.